Physics is the key to unlocking the secrets of the universe, and some equations have changed the way we understand reality forever. From describing the motion of planets to explaining quantum particles, these formulas are the foundation of science and technology. Welcome to my channel, everyone. In this video, we're counting down the top 6 most important equations in physics, the ones that truly change the world. Let's dive in. At number 6 is Newton's second law of motion. This equation, formulated by Sir Isaac Newton in the 17th century, is the cornerstone of classical mechanics. It states that the force acting on an object is equal to its mass multiplied by its acceleration. Why is it so significant? It explains how objects move when forces act on them, whether it's a car accelerating, a ball being thrown, or a rocket launching into space. Engineers use it to design everything from bridges to airplanes, making it essential for modern technology. Without this equation, our ability to predict and design motion would be impossible. At number 5, we have Maxwell's equations. These are 4 equations, read in their modern form as del dot E equals rho over epsilon naught, del dot B equals 0, del cross E equals negative partial B over partial T, del cross B equals mu naught, J plus mu naught epsilon naught partial E over partial T. Developed by James Clerk Maxwell in the 19th century, these 4 equations describe how electric and magnetic fields interact and propagate. Why are they groundbreaking? Maxwell's equations unified electricity and magnetism into a single theory, showing that light is an electromagnetic wave. Secondly, they laid the foundation for technologies like radios, Wi-Fi, cell phones, and even modern power grids. These equations also predicted the speed of light, paving the way for Einstein's theory of relativity. Maxwell's work transformed physics and showed the deep connections between forces we once thought were separate. At number 4 is the wave equation, written as partial squared psi over partial t squared equals v squared del squared psi. This equation describes how waves move through space and time. Whether it's sound, water, or light, this formula governs their behavior. Why is it so important? Well, it helps us understand phenomena like sound traveling through air, seismic waves during earthquakes, and even light bending through lenses. The wave equation is critical in quantum mechanics, where it forms the basis for understanding wave-particle duality. It's used in engineering, acoustics, and even medical imaging technologies like ultrasound. This simple yet powerful equation is everywhere, explaining the natural vibrations of the world around us. At number 3, we have Einstein's general relativity equation. This equation redefined gravity not as a force, but as the curvature of space-time itself, caused by mass and energy. Why is it revolutionary? It predicts black holes, gravitational waves, and the expansion of the universe. It explains how massive objects like the sun warp space-time, bending the path of light, a phenomenon confirmed during a solar eclipse in 1919. And it's the foundation of modern cosmology, helping us understand the Big Bang, dark matter, and dark energy. General relativity isn't just theoretical, it's practical. Without it, GPS technology wouldn't work because satellites experience different space-time curvatures than we do on Earth. At number 2 is another equation by Albert Einstein. E equals mc squared. This elegant formula states that energy, E, and mass, m, are interchangeable, connected by the speed of light squared, c squared. Why is this equation so important? It explains how stars shine, converting mass into energy through nuclear fusion. It underpins nuclear power and the development of atomic bombs, demonstrating the immense energy stored in even tiny amounts of matter. It's a universal truth, showing that mass and energy are 2 sides of the same coin. E equals mc squared is simple, profound, and one of the most famous equations in history. And finally, at number 1, we have Schrödinger's equation. This equation, introduced in 1926 by Erwin Schrödinger, is the foundation of quantum mechanics. It describes how quantum systems evolve over time. Why is it the most important? Well, the psi in the equation represents the wave function, which gives the probabilities of finding a particle in a certain place and state. Schrödinger's work explains phenomena at the atomic and subatomic levels, from how electrons orbit atoms to the behavior of particles in quantum computers. This equation has led to revolutionary technologies like semiconductors, lasers, and quantum computing. Without Schrödinger's equation, the quantum world and much of modern technology would remain a mystery. And there you have it, the top 6 most important equations in physics, each representing a giant leap in our understanding of the universe. From Newton's laws that describe motion to Schrödinger's equation that unlocks quantum mysteries, these formulas have shaped science, technology, and our view of reality itself. Which equation do you think is the most revolutionary? Let me know in the comments below. And don't forget to subscribe for more fascinating science content. Thanks for watching.